Today's lesson will be all about eddy currents. In a nutshell, eddy currents are currents that are induced within a conductor that is in the presence of a changing magnetic field. But to understand how they work, we must delve into the topics of electromagnetic induction and Lenz's law. We should know by now that when a current is applied to a conductor, the moving positively charged particles produces a magnetic field around said conductor. But the obverse can also happen. We can induce a current inside a conductor using a magnetic field. Take the example of this solenoid. Right now the coil of the solenoid is unpowered. When we move this north pole magnet towards it, a current will be produced in this direction. This induced current is called the EMF, or electromotive force, and it happens because the system tries to resist changes in magnetic flux. The solenoid is happy in this state with no magnetic fields and wants to stay that way, so when an external magnetic field arrives, it resists this change by creating a magnetic field in the opposite direction. This magnetic field comes from the induced current. We know the direction that this induced current will flow in because the magnetic field produced will always oppose the external change in flux, which is the basis of Lenz's law. Looking at the diagram, the magnet is moving in this direction. Using our right-hand curve rule, we point our thumb in the opposing direction, and we see that the current will flow in a clockwise motion. It is important to realize that the induced current does not come out of nowhere, otherwise it would violate the law of conservation of energy. The energy that is induced comes from the force that is required to overcome the resistance to changes in magnetic flux, remembering that this resistance comes from the opposing magnetic fields in the coil, generated from the induced current itself. Looking at Faraday's law, we can figure out how much current is induced. We can see that the electromotive force is equal to the number of turns in a coil, multiplied by the change in magnetic flux over the change in time. We can increase the electromotive force by increasing the number of coils, increasing the magnitude of the change of flux, and by changing the flux over a shorter amount of time. But induced currents don't just exist in wires. They can be produced in conductors of all shapes and sizes. Unlike wires though, the current can flow in any direction in a solid conductor, so we give this kind of current a special name: eddy currents. Eddy currents are small circular flows of current that are produced in the presence of a changing magnetic field. They occur when the conductor is large enough to support the circular flow of current. Let's take a square plate of metal and move it into this magnetic field. The eddy current will be produced at the boundary when the metal cuts across the magnetic field lines, since this is the point where the magnetic flux is changing. We can use the right-hand rule to figure out the direction of the EMF produced here. Field lines point in, plate moves to the right, the current points up, so the eddy current will be counterclockwise. Once again, the eddy currents create their own magnetic field, which opposes the change in flux. Therefore, there will be some resistance when the plate is being moved into the field, which is where the energy comes from. So far, eddy currents and magnetic induction sounds like an amazing idea. They are used in many applications, from cooking on induction stoves to electromagnetic braking on trains. But eddy currents are not always a good thing. One area where they are especially troublesome is the inside of transformers. Now, transformers are devices that utilize induction to increase or decrease a supplied alternating current, consisting of two solenoids wrapped around an iron core. One solenoid generates a constant change in magnetic flux sent through the iron core to induce an alternating current in the other solenoid. The fundamental principle of induction, which this device works upon, is also its weakness. The iron core required for a transformer is electrically conductive, and what happens to conductors in changing magnetic fields? That's right, eddy currents are produced. This is undesirable because the eddy currents here are not doing any useful work. These currents have nowhere to go and it is dissipated as heat. This reduces the output and the efficiency of the transformer, as ideally we want all of the current to be induced in the coil, but unfortunately some of the current ends up in the core itself and is wasted. If we don't try to reduce the eddy currents in transformers, not only will we have a terribly inefficient device, but it could possibly overheat and cause damage or injury. So how do we reduce eddy currents? One way we can do that is by changing the way we make the transformer core, creating what is known as a laminated core. By constructing the core out of plates, sandwiched together with non-conductive layers in between, and ensuring that these laminations are parallel to the change in flux. We decrease the cross-sectional area of the core that is perpendicular to the magnetic field, reducing the available area for an induced current, since only a magnetic field acting perpendicular to the conductor will create an EMF, reducing the magnitude of our eddy currents. A similar technique could have been used in my transformer to make it more efficient. I could have made my own core using washers and separated them with plastic sheets or another non-conductive material, creating what is effectively a laminated core.